For number 8 on the practice test, I'm asking you to find the equation of the tangent to a curve at a specific point. So in this case, the curve I gave you, and the same will be true on the test, is just a quadratic. We have y equals x squared plus 12x plus 27. And we want to know the equation of the tangent line at the ordered pair, negative 116. So we know in order to find the equation of a line, you need a point and you need a slope. We already have the point. So all we have to do in this problem is to go in and find the slope. In order to find the slope, I need to take the derivative of my function. When I do that, of course, derivative of x squared is 2x, derivative of 12x is 12. Now, you need to evaluate that derivative at the x value of interest. So this is a function y in terms of x. Well, the slope when x is -1 is going to be the derivative evaluated at -1. In this case, it gives us 2 times -1 plus the 12. And we can say, well, that's going to be -2 plus 12 for 10. I know the slope of the tangent line to this curve at this point has to have a slope of 10. As soon as I know that slope and that point, I plug those values into the point slope formula. Y minus y1 equals m times x minus x1. Now notice, y minus y1 becomes y minus 16. We have our slope 10 times the group x minus x1, which becomes x minus a -1, or better written as x plus 1. I distributed through the 10 on the right-hand side, and then I added 16 to both sides to get our final equation of the tangent line, y equals 10x plus 26. Not too bad. Now, the next problems are wanting us to use our derivative techniques that we learned in sections 3.2 through 3.6, where I'm asking you to find h prime of t if h of t is equal to 5 on the cube root of t plus 7 over the cube root of t. So the key to working this problem is to understand that the connection between the radical expression and the fractional exponents. Cube root of t means the first term has a t to the 1/3 power. And if you're dividing by the cube root of t, that means t to the 1/3 power, and it's the -1/3 power since it's in the denominator. Now, once you rewrite it in terms of fractional exponents, then you can say, well, okay, let's use the power rule. 1/3 comes down, multiplies the 5. Then we have t to the 1/3 minus 1 power. When you subtract 1 from 1/3, you get the -2/3 power there. For my second term, please notice it's a minus because you'd have a -1/3 times a 7 for a minus 7/3. T to the -1/3 minus 1 power becomes the -4/3 power there. Now I can say, okay, final answer needs to be back in the format of the original question. The original question is in our radical form, so my answer needs to be in radical form. T to the -2/3 power means the cube root of t to the second in the denominator. So you see I had to write the answer as 5 over 3 on the cube root of t to the second. Then I have minus 7/3, and I know that this t belongs in the denominator multiplying the 3, and it will be the cube root of t to the 4th in that denominator. Final answer there. For number 10, I'm asking you to use the product rule to take the derivative of x cubed d to the x. All right, product rule simply says that we need to take the derivative of the first term times the second. Well, derivative of x cubed is 3x squared times the second e to the x. Now, plus the first times the derivative of the second. But remember, e to the x is the only function we've seen whose derivative is itself. So you'd say, well, derivative of e to the x is just e to the x, and you could leave your answer here. A factored answer is always superior, and this one's very easily factorable, so I went ahead and did that. We could factor out an x squared e to the x amongst these terms, and when you do, you'd be left with 3 plus x. But again, I would give full credit for this answer. This answer is better though. Up next, you're asked to again use the product rule. This time I give you an expression that contains other letters. Notice I did not call them variables, other letters. You know the variable of differentiation always by looking at this. It's asking you to find the derivative with respect to x of this expression. Now, please remember, unlike the last problem where I could say f prime of x is equal to this, h prime of t is equal to this, you better not say d dx is equal to anything. d dx is an operator. The instant you start taking the derivative, you've done the operator, it goes away. So the correct notation for this problem, derivative with respect to x of this group is. So then I say, well, that derivative is the derivative of the first group, which derivative of a is 0, but the derivative of 2bx squared, the 2 comes out in front of the x, multiplies the constant coefficient of b, and I get 2bx to the first. So derivative of the first times the second plus the first group now times the derivative of the second. Well, AB is just a constant, so it has a derivative of 0. Derivative of x cubed is 3x squared. Now, the derivative has been taken correctly, but this answer is not sufficient because you should not have multiplication in an answer unless those terms are factors. None of these terms are factors, so I need to distribute and undo the multiplication to simplify. I distribute the 2bx throughout the first group, and I get 2ab squared x plus 2bx to the fourth. I distribute the 3x squared throughout the second group, and I would get 3ax squared plus 3bx to the fourth. And then there's really nothing you have to do at that point because I don't require factoring. So I would have been fine with this answer. Actually, let's see. It looks like there's some like terms. The second term and the fourth term are like terms. So I said 2bx to the fourth plus 3bx to the fourth was 5bx to the fourth. So you could just write this term plus 5bx to the fourth. Now, what I went ahead and did is, as I gathered like terms, I went ahead and also recognized that they all had a common variable of x. So I factored out the x, and then I had 2ab squared left for the first term. The second and fourth term combined to give me 5bx cubed after an x is factored out. And then the remaining term would just be 3ax after the x is factored out. This would be a gorgeous, fully factored final form of the final answer. Number 12, we have a quotient rule problem. So I said use the quotient rule to take the derivative of f of t. Now, unlike number 11, where I could not call d dx as my answer, derivative with respect to x of this expression is equal to this. So if somebody said, well, what can you call your answer? I can't call it anything. The original function was never named. Here, the original function is named. It's f of t. So its derivative can be named f prime of t. So now I can say, well, all right, I have the original function f of t. Its derivative f prime of t would equal, I always know, go ahead and square the denominator anytime you're using quotient rule. Then bring that denominator up to the numerator times the derivative of the numerator. Well, the derivative of t to the fourth would be 4t cubed. That's our power rule. So this is denominator times derivative of the numerator minus the numerator, t to the fourth, times the derivative of the denominator. Derivative of 1 plus e to the t, we know derivative of 1 is 0. Derivative of e to the t, simply e to the t. Now, please don't leave your answer like this. Again, there's multiplication going on in that numerator on terms that are not factors. That's not fully simplified. I need to distribute the 4t cubed throughout the first group, the t to the fourth throughout the second group. And this answer would be fine. I'm okay with that. At least it doesn't have any multiplication going on on terms that are not factors. Now, if you did want to get a superior answer, you could say, well, notice all three terms in the numerator have a common factor of t cubed. So I went ahead and factored out the t cubed, and it left me with 4 plus 4e to the t minus t e to the t all over my denominator. Now, for the next one, it's another quotient rule problem. This time it involves trigonometric functions. We have y is equal to 3 cosine x minus 4 over the sine of x. So when we take the derivative, again, you can name this derivative. The original function was named y. Our derivative is going to be named y prime. Okay, so the derivative tells me every time square the denominator. Bring that denominator up to the numerator times the derivative of the numerator. The derivative of 3 cosine is going to be 3 times a negative sine, which is better written as negative 3 sine x. That parentheses absolutely mandatory there. Otherwise, it looks like sine x minus 3 sine x, and it is not that. There's a multiplication going on there. So this is low d high minus the high function, 3 cosine x minus 4, d low, derivative of sine is cosine. So now, derivative has been taken correctly. But if you stopped at this step right here, I would count off 30% credit because it has not been simplified. The simplification, you cannot have multiplication unless those terms are factors. There's none of those terms in the numerator are factors. They're not multiplying everything else in the numerator. So go ahead and carry out the multiplication on the terms. We'll have negative 3 sine squared x in the first term. And the second product, I can see cosine x is multiplying this binomial, but then I'll take that product and subtract each term. So cosine times 3 cosine is 3 cosine squared x, but it's going to be subtracted. That's where that comes from. Then I would have a minus 4 cosine x, but you're subtracting it, so it becomes plus 4 cosine x. This answer would have been absolutely fine. So again, full credit if you get to here. I saw something that was kind of neat. I said, well, anytime I have the same coefficient in front of a sine squared and a cosine squared, I know I could factor that out. And the reason I would want to is because now sine squared plus cosine squared is a factor of 1. So this is just negative 3 times 1 plus 4 cosine x. That's better written as 4 cosine x minus 3 in your numerator over that denominator. So this would be the gorgeous answer. However, if you're just saying, what do I need to do to get full credit? Full credit would be this answer right here. So you don't have to use the trig identities to simplify them down if you don't want to. But I would not like this one because you have multiplication going on, even though those terms are not factors. For number 14, we have 5ax over bx squared plus c, and we're asked to take the derivative. So I said, okay, every single time I square that denominator in the quotient rule, and please notice every single time I'm just leaving the denominator as it is. I never tamper with it. So I don't actually physically go in and square that out by fulling it. That would be an inferior answer, not a better answer. So we leave the denominator as just a group squared. Then we say, okay, bring that denominator up to the numerator times the derivative of the numerator. Well, the derivative of 5ax would just be 5a. And then minus the numerator, 5ax, times the derivative of the denominator. I look at my denominator, bx squared plus c. That 2 would come down, multiply the b. I get 2bx to the first. Derivative of any constant is 0. So derivative of the denominator is simply 2bx. Now I can say, okay, again, though, I have terms being multiplied in the numerator and they're not factors. So those multiplications need to be undone. I distribute 5a through the first group. I get 5abx squared plus 5ac. And then in the second group, when I multiply, I'll get minus 10abx to the second. So then I recognize that I have an abx to the second and another abx to the second. So the first and third term combined, and I would have a total of negative 5abx to the second. I went ahead and combined those and factored in the same step. I said, well, okay, I also have a common factor of 5 that I can pull out of all terms and a common factor of a that can be pulled out of all terms. When I do that, this term would be left with just a c, and then the first and third are going to combine to be minus 5 ab x to the second. When you factor out the 5a, you just get minus b x to the second. So that's the fully factored final form of the fantastic answer. However, I would have been okay with this form, not this form, but I would have been okay with this form. Best form right here. Number 15. When we're asked to take the derivative of this product rule expression, we say, well, okay, we first do have to recognize that it is the product rule. You have the differentiable function 12 secant theta times the differentiable function tangent theta. So we say, okay, now this one's a little tricky because the derivative of secant is secant tangent. So when I say the derivative of the first, derivative of 12 secant theta is 12 secant theta tangent theta. So this is derivative of the first times the second. Now, plus the first 12 secant theta times the derivative of the second. Derivative of tangent is secant squared. So here is my derivative. And then I just said, well, I can pretty nicely simplify this. I could factor out this expression because they both have a 12 secant theta as a factor. I factored that out. When I do, I'll be left with tangent theta times tangent theta for tangent squared theta for the first term. And then the second term, if I factor out the 12 secant theta, you're just left with a plus secant squared theta, fully factored final form of the answer. For number 16, again, I threw some other letters at you. That shouldn't be too bad, though, whenever we're thinking about it. We just have y equals a secant t plus 3b cosecant t. So I can say, well, all right, this is a constant times a one of our differentiable trigonometric functions. We know, like we saw in the last problem, derivative of secant is going to be secant tangent. So derivative of secant t is secant t tangent t. Derivative of that first term is just going to be a secant t tangent t. And then for my next term, I just had to think, okay, 3b, that's just a constant coefficient times the cosecant function. Well, derivative of cosecant is negative cosecant t cotangent t. So the fact that derivative of cosecant is going to be negative is going to go out and change the sign in front and make this minus 3b cosecant t cotangent t. And that's all you have to do. There's no common factors or anything left like there were in several of our other problems. For number 17, this is where I guarantee you'll have the 3-term product rule to consider. In this one, I do need you to understand that I have the differentiable function 2x to the 5th times the differentiable function e to the x times the differentiable function cotangent x. So now, whenever you're taking the derivative there, you'd say, well, okay, the way I take the derivative, no matter how many times there are, is to go in and say derivative of the first term times everything else, derivative of the second term times everything else, derivative of the third term times everything else. That's precisely what I'll do here, guys. I'll say, okay, derivative of 2x to the 5th is going to be 5 times 2 for 10 x to the 4th. I get 10x to the 4th, and then notice second and third term just come down. For the second term in here, I'll say plus 2x to the 5th times the derivative of the second, but derivative of e to the x is just e to the x times the third, plus in the third term in your expression, you'll say, well, the first term times the second term left alone times the derivative of the third. And then you say, well, derivative of cotangent is negative cosecant squared x. And again, in this format, you'd have to have the parentheses. Otherwise, it would look like you're subtracting cosecant squared. So I can say, okay, this is a good answer. To go from that good answer to a great answer, you'd need to factor. And what I did there is I just said, well, notice you have a constant factor of 2 in all of the terms. You have a variable factor of x to the fourth in common in all of the terms, and you have the exponential function e to the x. So if I factor out 2x to the fourth e to the x, my first term is going to be left with a 5 cotangent x. My second term has an x to the first remaining along with a cotangent x. And then the third term, please remember that minus comes out, changes the positive to a negative sign there. So we say minus, and it has a factor of x left along with that cosecant squared x. Fully factored, gorgeous final form of the answer there. Now, for the last question, again, I'm wanting you to be able to understand the connection between graphs and their derivatives. So for this one, I actually think it's easier to work from the derivative and find the graph. So if I were to say, okay, look at this derivative with me here. In this graph, what do I know about the function that this is the derivative of? Well, I know the derivative never gets negative and it never even hits 0. Derivative is always positive. So I know the function it's the derivative of is always increasing. Its rate of increase gets the smallest right around x equals -1. So it'll be increasing rapidly, then increasing slowly, then increasing rapidly again. There's only one function here that does anything remotely like that. Please notice the graph of D is always increasing, always has positive slope. The slope would be greater through here. It's still a positive slope, but it's not as extremely positive around -1, and then it starts to get more steep again. So I can easily say this first one has to represent the derivative of D. Now for my next one, when I'm looking at it and saying, okay, what function does it represent the derivative of? If I were thinking about it, I can say, well, whatever function it represents the derivative of, this derivative starts out positive. So the function it's going to represent is going to start out increasing. It's going to flatten out at 2. Since this derivative turns negative between -2 and 0, its function that it represents is going to decrease between -2 and 0, and then start increasing again. Wherever a derivative is positive, the original function increases. Wherever a derivative is negative, the original function decreases. Whenever a derivative has an x-intercept, the original function flattens out and normally obtains a maximum or minimum value. So please notice the function's right here. You can say when this is positive, well, this function is increasing. In this region where the derivative is negative, well, this function decreased from -2 to 0. Flattened out at 0 because this had an x-intercept at 0. Then when the derivative turned positive, this function turned increasing. So this is right underneath the function it's the derivative of. It's b prime of x. For my next one here, it's kind of the reverse scenario of the one preceding it. It's going to represent a function that starts off decreasing until x gets to -2. Then the function is going to increase between -2 and 0. Then the function is going to decrease again from 0 to infinity. Please notice right up here, this function decreases until -2. At -2, it flattens off since the derivative is 0. From -2 to 0, it increases because this derivative was positive. Flattens off at flattens off at 0 because the derivative is 0 at 0. And then after 0, it turns decreasing. Well, that's because this derivative here is negative. So again, it's right underneath the function it's the derivative of. And the last one obviously has to be by process of elimination, a prime of x, but think about why. I know that this function should only, the function it's the derivative of should only flatten off once because it only has one x-intercept. This function, the function that it's the derivative of should be increasing for all x values before 0. It should be decreasing for all x values after 0. So I said, well, then it's going to be a parabola, and then the parabola is going to be pointing downward. It's going to be increasing for all values before 0, decreasing after 0. it's got to be that. So notice I don't know the specific y values of the original function, but I know the shape of the original function. I knew that this had to represent a function that was increasing before 0 and decreasing after 0, simply because of what I knew about the derivative graph. So this had to be a prime of x. All right, guys, that should give you a very good preparation for this second test. As always, please let me know if you have any questions. Be glad to help out however I can.